I want to do an example under the conditions of one dimension and constant acceleration. In particular, I'd like to use this example to demonstrate sort of a strategy in solving problems. Now, there is no flow chart or set of procedures that's going to help you solve any type of problem. But assuming you don't have an exercise, something where when you read it, you can immediately write down the answer, something that you have to think through, a good way to approach the problem is using these 4 steps. First is to visualize, the second brainstorm, and then solve and check. And I'm going to highlight sort of how to go through that process with this particular problem. This one is vague and it requires the person solving it to make a lot of decisions, and we'll demonstrate that here. So the problem is this. A ball is thrown up at the same time another ball is dropped above it. They collide when the thrown ball has twice the speed of the dropped ball. Where do they collide? So I would challenge anyone to just be able to read that and write down the equation that's going to give them the answer. This really requires us to do some thinking. So the first step is to clearly visualize what's going on. And my first part of visualization is pictures and sketches. Okay, so I have some ball that's up high, another one that's low. This one is going to be thrown up. This one's going to be dropped. And then somewhere in the middle, they're going to collide. And so this is here. This is the point where they collide. Okay. And so here, I think the picture is pretty easy. And more than a picture, you should have in your head a visualization of what's happening. And that will help you later on extract information from the problem. A lot of time you have to create relationships between parameters that aren't given as physics equations, but just derived logically from the problem itself. And so, okay, so I have, and you do that by being able to picture what's going on clearly in your mind. All right, so I have this ball being thrown up, ball being dropped, and they collide. As part of a picture, in this visualization, I want a schematic. And schematics almost always have coordinate systems. And a coordinate system requires a positive direction and a 0. I get to choose that. And so for this, I'm going to choose, absent anything else, 0 to be at the point where the first ball is released, and I'm going to have positive x going up. All right. So let's see. Having a good idea of sort of what's going to happen, at this point, I sort of moved on to the brainstorm section. And a lot of times I'll go back and forth. I might have to draw more pictures as I brainstorm a little bit. Part of the brainstorming part of solving the problem is going to be what sort of physics applies to this problem, what sort of model do I want, what sort of approximations am I going to make. And in a problem like this, some of these are pretty straightforward, but this becomes more complex as you learn more physics. So sort of the physics that applies, I think we've studied our constant acceleration equations, so I think we'll be using those. We're going to use the particle model, of course, represent these balls by individual points. We've got constant acceleration is going to be our approximation. We're ignoring any sort of air resistance or any other acceleration other than the acceleration due to gravity. And so that's part of the approximation. And so that leads us to the idea that we're going to be able to apply our constant acceleration equations. Okay, so let's go ahead and get that down. So the physics that we're going to use is, if we have from our constant acceleration equations, our final velocity in the x direction is equal to our initial velocity plus the acceleration, which is constant, times the time interval between 2 points in time. Our final position is equal to our initial position plus our initial velocity times our time interval plus 1/2 times our acceleration times our time interval squared. And a third useful equation is that our final velocity squared is equal to our initial velocity squared plus twice the acceleration times the displacement between these 2 points in time. So remember, these are derived equations, and what is key is that they only apply for 2 specific points in time. So part of our brainstorming approach to this problem is that we have to clearly identify in our mind what those 2 points in time are. Okay. And so here I think it's fairly straightforward. We're going to have our initial time to be the moment that each ball is released, and we'll call that our initial time, t is equal to 0. And then our final time is going to be the time when they collide. And so I don't have to write t sub f all the time. I'm just going to give that some constant t. This is now not an independent variable. This is a specific time t. It's the final time, the time when they collide. I've given the initial time to be equal to 0. The other thing you'll notice when I wrote these is I didn't call this v sub xf or v sub xi or x sub f or x naught or xi. These are the initial, this is the final velocity, initial velocity, final position, initial position. It's, with all these equations and all these parameters, it's easy to get confused about what all of these things mean. This is why it's critically important that even then when you write x sub f, in your mind you read final position. So as you have those definitions in your mind, then it's much easier to keep them straight as you solve the problem. Okay, so we have some physics that we're going to apply to the problem. We've got some approximations, model, all of those things. The next part of the brainstorming session is sort of what do you know? What do you not know? And by doing these things, then we can establish relationships between what we know and not know. And then once we have enough of them, we can move on to, we can develop a plan and move on to being able to solve the problem. Okay, so in a problem like this, I just like to start listing things. We have our time interval. That's equal to t, right? That's just equal to tf minus ti. So we know that already. Let's go ahead and make lists for each particle. I'm going to call this ball particle 1, this ball particle 2. Again, the problem didn't tell us which one that was, and so we get to name that ourselves. Okay, so for the first particle, I want to establish relationships. Let's determine what its initial position is. So I have x sub 1i, so initial position of particle 1. Well, from my coordinate system, I can see that that's 0. I'm also interested in the final position of particle 1. I'll call that x sub 1f, and that's at the point where they collide. Well, what do I want to call that? I'm going to go ahead and just call that x, because that's going to be an important parameter. That's what I'm looking to solve for. And it's going to be some value of x. I don't know exactly what it is, and so I'm going to call that. Again, this is not now an independent variable. It's the final position in x that I'm trying to solve for. Okay. So what else do I know about the first particle? So the initial velocity is unknown. It says it's launched with something, but I don't know what that is. And the initial velocity, sorry, is that I'll call v sub 1i. V sub 1f is its final velocity, and I don't know what that is either. I was told that the speed of 1 is twice the speed of 2, but exactly what that speed is I don't know, so I'll have to come to that later. And then finally I know the acceleration. The acceleration is constant. The magnitude of the acceleration is g. Acceleration is a vector, and so it has a direction. And to understand that direction, I have to go back to the coordinate system. The free fall acceleration direction is defined as toward the center of the Earth. And so with this coordinate system, A is pointing down in the negative x direction. So I would call A to be, would have a value of negative g, where g is the magnitude of the free fall acceleration. And of course, there's the time, and the time is unknown. Okay, so what do I know about particle 2? So, where is its initial position initial position of particle 2? I don't know where that is either. I'm going to give it a name, and I'm going to say it starts out at some height h. I mean, we need to know where they collide, and it's going to collide relative to to where I dropped it from. So I'm going to give it a name. So again, this is the sort of thing you do. The problem didn't say particle 2 is dropped from a height h. It says that a ball was dropped, and so I get to describe that notation. I get to define the notation, and I'm going to define it in a way that it's meaningful to me. I call that particle 2, and I'm going to say it's dropped from a height h. Okay, so what else do I know? So what is the final position of particle 2? Well, its final position is the same as the final position of 1, because the point in time I'm looking at is the point where they collide. And so this brings up an interesting point. To do this, I used the relationship that the final position of 1 is equal to the final position of 2. You know, this isn't a physics equation. You're not going to find this in the book. It's not a and it's not given in the problem. It's a relationship between variables that we extracted from the context of the problem using logic. And that's the sort of thing that you have to do to be able to solve physics problems. A lot of times you have to create relationships and extract that knowledge from the problem itself, which is why it's so important to have good pictures and schematics and a clear visualization of what's happening. Okay, so what else do I know? So I know the initial velocity of 2? I do, because it was dropped from rest, so its initial velocity is 0. Do I know the final velocity of 2? I don't. I know that it's half the speed of 1. So its acceleration, it's in free fall, so it's also equal to negative g. The time, I don't know. So at this point, I'm going to make another decision. I'm going to call the speed of that the second particle has to be v, and because I know that the final speed of particle 1 is twice that, so that's 2v. Now remember, I know the relationships between the speed. Velocity is a vector, so I have to go back to the diagram to assign the direction of the velocity. And so when they collide, the velocity of the first ball is up, so it's positive, and the velocity of the second ball is down, so it's negative. And so again, that information I extract from the context of the problem as well as my coordinate system to be able to identify the right magnitudes and signs of the final velocity of particle 1 and 2. All right. So I have now a lot of things that I know and don't know, and I know that these equations apply to this problem, so I'm going to start using these to see how I can establish relationships between them. You know, I have a lot of parameters and a lot of equations. I don't have a clear idea of how to solve, but I think if I start looking at these relationships, I'm gonna see what I can find. Okay, so the first, I'm going to look at this. Let's just look at the first equation. So I have the final velocity of the first one squared is equal to the initial velocity. Oh, sorry. Let's use the first one here. which is the final velocity, is equal to the initial velocity of 1 plus the acceleration times time. And we also have that the final velocity of 2 is equal to the initial velocity of 2, which is 0, plus the acceleration times time. And that's interesting. So this this is equal to 2 times speed v, and the final velocity of 2 is equal to negative v. So this might help establish relationships between the first and the second ball. But let's go on. I want to find position. I don't have equations for positions yet. So let's go on to this relationship and see what information that gives us. Really, this is, as the way I look at it, I'm still sort of in brainstorming stage. I'm just sort of seeing how these relationships work with each other. So the final position of particle 1, which is x, is equal to its initial position, which is 0, plus its initial velocity times time, plus 1/2 its acceleration times time squared. Really, this is the time interval, but I know that the time interval has, given how I've defined the times, is just equal to this t, the final time. Right. And the final position of particle 2, which is also x, is equal to its initial position, which is h, plus its initial velocity times time, which is 0, plus 1/2 at squared. So that brings me to the first interesting point, is that these two are the same parameter, x, which means the right side of these equations are equal to each other. If I set these two equations equal to each other, and the 1/2 at squareds cancel, I get that equal to each other. I get h is equal to v1 t. So I would think for a minute to see what exactly that means. It means that the time between the initial launch and the collision, the time to go from here to here, is the same as the time it would have taken the first ball at its initial velocity to travel the entire distance h if there weren't any acceleration. This is the zero acceleration equation. Distance is velocity times time. I think that's kind of interesting. I might not have guessed that originally. Okay, so let's see what we have now. I have here relationships for this final position in terms of h. What I don't have is time or the initial velocity. But I have these equations up here that relate that information. Okay, so if I look back at these two and combine them, I get twice the velocity is equal to the velocity 1 initial plus at. If I substitute at from the second equation, at is equal to negative v. So this tells me that my initial velocity is equal to 3v. So now I've learned something new. My initial velocity is 3v. Okay, now given this, I could substitute that into this expression here. I can solve for that and then see if I can find a relationship between x and my original height, h. Okay. Before I go any further, let's see if we can bring, still don't have a clear idea of the solution. So let's go back and bring in our third expression, just to see. We've learned some interesting things so far, and let's see with our third expression what that gives us. Okay, our third expression says that our initial velocity squared, our final velocity squared, sorry, for 1 is equal to our initial velocity squared plus 2 times a times the position difference for particle 1. And the position, the displacement, is x minus 0. So that's just x. And our final velocity for 2 is equal to the initial velocity, which is 0, plus twice the acceleration times its displacement. And 2, the displacement, is the final minus the initial. Its final is x, and its initial is h. So that's x minus h. And so now that I have expressions for my initial velocity and my final velocity, I think I can substitute into these equations and get a relationship between x and h. So let's go ahead and do that. So using our first expression, I have 2v squared, which is the final velocity, is equal to the initial velocity, which is 3v squared, minus 2gx. I've substituted in a is equal to negative g. And then for the second equation here, I have the final velocity, which is v squared, is equal to a negative 2g x minus h. All right, so if I just solve here, this gives me 4v squared is equal to 9v squared minus 2gx. And here we have v squared is equal to minus 2gx plus 2gh. And I think I can solve this now for v squared. If I substitute that into here for v squared, I eliminate v squared, and I'm left with x and h, and I should be able to find what the position that they hit, x relative to h. Okay, so if I solve this, this gives me 5v squared is equal to 2gx, or v squared is equal to 2/5 gx. So that's equal to minus 2gx plus 2gh. So this, if I bring this to the other side, this is 2/5 gx plus 2gx is equal to 2gh. Well, first, look, the g's cancel. And so 2 is 10/5. So that gives me 12 fifths x is equal to 2h. And then I can cross multiply, and x over h is equal to 5/6. So the fraction of the height, I can also rewrite this, x is equal to 5/6 h. And so the fraction of the height where the balls hit is 5/6 the distance from which the first ball was dropped.